We shall start now. In today's lecture, we do have only one questions. It's for the calculation of the settlements of the pile raft foundation systems. So for these systems, we're gonna consider the settlements of the raft by itself, and then for the pile group, and then we're gonna combine the settlement of the both systems, the raft and the pile group, to account for the combinations of the settlements from both structure, the raft and the pile, and we should have a considerable decrease in the amount of settlements as a result of these combinations, and more bearing capacity as well, because we'll have some bearing capacity from the raft by itself and some bearing capacity from the pile group as well. So the system should withstand more working load, and it should experience less settlement as well. So in these questions, we do have pile raft foundations. We need to construct the trilinear load displacement response using the Poulos and Davis approach to solve these problems, to consider both structure, the raft and the piled group. In here we do have six piles. Okay, this is the plan view of the piles, and this is the cross section of the piles. The size of the flexible raft, this is a flexible raft, so we need to consider the flexible raft scenario. It's not a rigid, so it's 2.5 meter by 5 meter, so this dimension is 2.5 meter and the long dimension is 5 meter. The spacing between piles center to center is 1.5 meter, so center to center 1.5 meter in this direction, and this direction 1.5 meter as well. The design load acting on the raft is 5 meganewton. So we have a working load acting perpendicularly into the raft systems, into the raft pile systems, 5 meganewton. We need to work out the settlements of the piled raft foundation systems, considering the diameter of each pile as 300 millimeter and the length of each pile 7.5 meters. So we do have identical piles here. A load test gave 15 millimeter settlements at 500 kilonewtons. So this is for the calculation of rho naught, which is the settlements of single pile under 1 kilonewton. Poisson ratio of the soil is 0.5 and the Young modulus of the soil is 40 megapascal. So we only have one soil in this problem, and it's clayey soils. Assuming that the ridge stratum lies far below the base of the pile, so we don't have any ridge stratum, so this is a floating pile scenario. Calculate the settlement of the pile raft foundation system considering the underlying shear strength of the clay layer as 75 kilopascal and the average reduction factor as 0.4. If we don't have this value, then we need to calculate it using the chart as what we have done in last tutorial. This is the formula for the settlement of the rectangular raft alone, because as we said, to calculate the settlement of the piled raft foundation system, we need to consider the raft by itself and the pile group by itself. So we need to calculate the settlement of from the raft, and then to calculate the settlement from the pile group, and then to add these two values together to calculate for the piled raft foundation systems. So this is the formula we need to use to calculate the settlements due to the raft alone. This is the amount of the pressure due to the working load on the raft Q, and this is the width of the foundation B, which is in our case here 2.5 meter, and we have 1 minus Poisson ratio. Poisson ratio here is 0.5, and we have the influence factor, which is IS. We're gonna calculate it using the formula, and the Q is the pressure applied on the raft, which is the working load acting on the raft by itself, but that's minus the load taken by the pile group systems. So we'll calculate this. This is the last thing to calculate in the problems. where P is the lesser dimensions, which is 2.5 meter, because we have 2.5 by 5 meters, so we need to consider the lesser dimension of the rectangle, which is 2.5 meter in our case here. Okay, and this is the influence factor for vertical displacements. This is the influence factor here for the vertical displacement under a flexible area carrying a uniform pressure. So depending on the shape here, for the rectangular we do have here two values depending on the ratio between length to the width and length to the width here. If the length to the width is 2, which is here 5 divided by 2.5 meter, that's 2. So we calculate here the value of IS. Instead of using the formula, we can use this table to calculate the value of IS, and in our case here it's 1.3. In our case here it's 1.3 because we have the ratio of length to the width ratio of the raft as 2, so that will give us the value of IS in our case here as 1.3. Okay, so now we'll go to the solutions and we'll analyze the problem. So firstly, as you can see here, we need to check what's the load carrying capacity of the raft by itself. So we need to consider that we don't have the piles in the problem, we only have the raft, and we need to find out if the raft by itself without the pile will carry the working load. And we need to remember that the amount of carrying load we have here is 5 meganewton. So we have a carrying load as 5 meganewton. Okay, so we need to calculate for this raft without the piles what's the ultimate bearing capacity. What's the ultimate bearing capacity? And then we need to divide the ultimate bearing capacity by the working load and to find the factor of safety. And we know that for the foundation problem we need to get a factor of safety around 2.5 to consider that that foundation is able to support the working load. If we got a factor of safety less than 2.5, then we need to redesign the raft or to add the piles to the problem to support more working load. So we're going to use this equations, which is the Terzaghi equations or the Meyerhof equations, to calculate the load carrying capacity, and which is half of the gamma, B and gamma. These are this is the formula of Meyerhof. So we need to substitute the values in this formula, and then we need to find what are the bearing capacity factor N gamma and C and NQ, considering the value of the friction angle in the problem as 0 because we have a clay layer, so the friction angle will be 0. And then if we go to this chart here, we can calculate for the friction angle equals 0. We can calculate what are the values of NC, NQ and N gamma. As we can see, NQ and N gamma are both 0. For phi prime equals 0, NQ and N gamma would equal 0. So that would cancel this term and this term. So what we're gonna end up with, Q ultimate would equal only the underend shear strength Cu multiplied by the NC factor, the bearing capacity factor NC, and the NC for phi prime equal 0 is 5.14. So in this problem, the ultimate bearing capacity Q ultimate is equivalent to 5.14, which is NC value for phi prime equals 0, and that's multiplied by the underend shear strength, which is in our case here is given as 75 kilopascal. So we need to multiply 5.14 by 75 kilopascal, and that will give us the ultimate bearing capacity for the raft itself, and that will be 385.5 kilopascal. And to calculate the ultimate load, the ultimate load carrying capacity, we need to multiply by the cross-sectional area of the raft, which is 2.5 by 5 meter. So we multiply this number, which is the ultimate bearing capacity, by the area to find what's the load carrying capacity, because this is a stress value, so we need to calculate what's the load value, the load carrying capacity of this raft by itself, and that will be 4.8 meganewton. And we need to remember that the working load is 5 meganewton, so we got the load carrying capacity as 4.82 and the working load is 5 meganewton. So if we divide 4.82 by 5, the factor of safety will be the inverse of this value, so you just need to correct this one. So it's 4.82 divided by 5, and that will be less than 1. So the factor of safety is too far from the satisfactory value, which is 2.5. So the raft by itself will not be enough to support the working load 5 meganewton, and that's why we need either to redesign the raft if we have the capacity to do so on the site, but the cheaper solutions will be to add the piles to the problem, and that's what we have done here. We add group of piles, which are 6 here in this layout, attached to the raft, as we can see here, and they're both sitting on the ground. So this is the ground level, and the raft and the pile will be sitting on the ground. So the load carrying capacity of the whole system will be part of the raft, and part of that will be due to the pile group systems. So we have calculated what's the load carrying capacity of the raft by itself. So we need to remember this number, which is 4.82, and then we need to calculate the one coming from the pile group systems. And the one coming from the pile group system, as what we have done in the last 2 tutorials, we need to consider both scenarios. The first scenario, we need to consider the single pile failure approach, and then we need to consider that the piles on the system, the 6 piles on the systems, will fail as one block. So and obviously this is the formula to calculate for the load carrying capacity for the pile on the systems, which is PU is equivalent to the PPU, which is the end bearing resistance plus the shaft resistance. And because we are dealing here with a clay layer, so the end bearing resistance will be equivalent to the under-end shear strength multiplied by NC value, and that's all multiplied by the cross-sectional area of the pile, which is AB, and here we have circular cross-section, so that will be the area of the circle of each pile, and that's plus the shaft resistance, which is the shaft area, which is AS, multiplied by the alpha and CU, the reduction factor, and the CU value, the under-end shear strength of the soil. So if we substitute all these values together, but before that we need to calculate the value of NC, and to calculate the value of NC we need to calculate the value of L over D, the length of the pile over the diameter of the pile. So that will be 7.5 meter, the length of the pile, each pile, and the diameter of each pile is 0.3 or 300 millimeter, and that will give us 25. And if we use the chart, as you remember, any value more than 3.5 as L over D will give us NC value is equivalent to 9. So we got here the value of NC as 9, and then if we put everything back into these equations, the CU value as 75, the under-end shear strength, the NC value as 9, as we calculated from the previous steps, and the cross-sectional area of the circle of the pile pile base, which is pi by the diameter square divided by 4, and that's plus the shaft area, which is pi by the perimeter, and the perimeter is the length of the pile. That's the length of the pile, and the perimeter is pi multiplied by D value, and that's multiplied by the reduction factor, which is alpha, multiplied by the under-end shear strength, which is 75 in our case here. And in here the value of alpha is already given in this equation here. As you can see, the average reduction factor throughout the length of the pile is given as 0.4, so we just need to substitute this value back into equations, and that will give us that the load carrying capacity of each pile, of the single pile, is 259.771 kilo Newton. And for the group systems, we need to multiply this number by the number of the pile in the problem, which are 6. So if we multiply this number by 6, that will give us 1.56 meganewtons. That's for the pile group system, considering the single pile approach. We found the load carrying capacity using the single pile approach, and it was 1.56 meganewton. Then we need to go to the block failure scenario, and it's the same equations. We just need to check the value of NC, and then to change the value of cross-sectional area, and to change the value of the shaft area. So these are the things we need to change from the previous equations, but we need to use the same value of underend shear strength, the same value of alpha. So it's only the value of NC we need to recheck it, because we are considering now the whole area encompassing the whole piles in the problem, which are 6 here. So we need first to find out what's the area of the block systems, and to find out that we need to find what's the influence area of each pile. So we do have here the spacing between the two piles as 1.5 meter, and that will be 1.25 meter. So that will be altogether 3 meter. And we need to add the diameter of each pile, which is 0.3. So the dimension in this direction will be 3.3 meter. And the dimension on that directions will be 1.5 plus 0.3, so that will be 1.8 meter. So we have the dimension of the block systems as 3.3, that's the long dimensions, and the short dimension will be 1.8 meter. So if we use both values here in this equation to calculate L over D, to calculate NC value, then we got 2.27 and 4.167. If you use this value, if we use this value in the chart, that will give us NC value equivalent to 9. But if we use this value 2.27 in the chart, that will give us a value of NC less than 9. So we need to consider this value, because that will give us saver scenario or saver approach, which is the worst scenario for the design values. So the value of NC here, we found it from the chart. It's the same as what the chart we use in the last two tutorials. That will be 8.5. And then we need to put everything back into equations. The PU will be equivalent to alpha, which is 0.4, multiplied by the CU, which is 75 kilopascal. And that's multiplied by the shaft area, which is the perimeter area, which is 3.3 plus 3.3 plus 1.8 plus 1.8, so that's 3.3 plus 1.8 multiplied by 2. This is the perimeter area of the rectangle here of the block systems. That's multiplied by the pile length, which is 7.5, or for the group length, which is 7.5 meter in the Z direction or in the elevation directions. And that's plus the end bearing resistance, which is CU value, 75 multiplied by 8.5, the NC value, and that's multiplied by the block area, block cross-section area, which is 3.3 multiplied by 1.8, and that will give us 6.20 Newton. If we compare these two values together, the 6.1 meganewton with the 1.56 meganewton, then we need to choose the lesser value as the load carrying capacity of the pile group systems. And in our case here, we're gonna consider the 1.56 meganewton. So what we have got here, we got for the pile group system, we got 1.56 meganewton, and we got another 4.82 meganewton from the raft by itself. So the load carrying capacity of the whole system will be 4.82 meganewton plus 1.56 meganewton, and that will be subjected to a working load which is 5 meganewton. And still it's not sufficient, because if we add this value here, 1.56 plus 4.82, and that's all divided by 5, then it will not be more than 1.5. So we still need more load carrying capacity to support the working load. So still the system is not sufficient to support the load, but we're gonna continue to find out the settlement of the whole systems. So still the criteria for the load is not satisfied. Now we need to check the settlement for the whole group. And to check the settlement of the whole group, as you remember from the lecture you talk with Samanthika, for the whole systems that will be two parts. So we do have the settlements due to the to the pile, and we do have the settlement due to the raft. So we need to calculate the settlement due to the pile group, and we need to calculate the settlement due to the raft, and then to add these two values together to work out solutions like this one here. We can have it in this chart here. So we need to have something like this chart here. So we have the settlement here, and the settlement will be composed of two parts, as we can see here, according to the curve 1, which we are working in here, and the working load here will be due to the load carried by the piles and the load carried by the raft, and then the settlement will be due to the two components as well, which are the pile and the raft. So we need to do something similar, and to do that we need first to calculate the settlement due to the pile group, and once we have done from that we need to calculate the settlement due to the raft systems according to this equation here. But first we need to calculate the settlement due to the pile group, and we know that due to the pile group we need to follow the procedure described in your lecture. And to do so, we need to, that's according to the Poisson approximations, we need first to find the effective cap area for one pile, because now we are not considering the pile as individual pile, as only the pile area. We are considering the cap area at the top of each pile, and to do so we need to find what's the diameter of this cap. And the diameter of this cap, because we do have here the raft area as 2.5 meter by 5 meter, so that will be 2.5 meter multiplied by 5 meter, and then we need to find what's the DC value. So we have here 6 pile in the problem, and we need to apply this equations, which is the area of the circle of the cap, which is pi multiplied by DC square, that's divided by 4. So we only have here one unknown value, which is the DC value. So the DC value for this scenario, considering 6 piles and the cross-sectional area of the raft 2.5 or by 5 meter, will be 1.62 meter. Then we need to calculate the DC over D ratio. DC over D ratio will be useful to calculate the value of RC value and other values as well. The RC value, which is the settlement of the cap unit divided by the settlement of the freestanding pile. But in here we are considering the settlement of the cap unit, okay? Because using the Poisson approximations, we need to calculate the settlement for the cap unit, not the settlement for the freestanding pile, because we are considering both scenarios, the raft and the pile. So we need to calculate this value. So we need to calculate what's the RC value, or the reduction factor here, the RC value. So to calculate the RC value, we need obviously to use this chart here, the same as what you have taken your lecture. It will be this chart, the RC value, and to calculate the RC value we need to find out what's the value of DC over D. We have already calculated the value of DC as 1.629. Then we need to divide this value by the diameter of each pile, which is 0.3 meter. So we calculate the value of DC over D as 5.4, and then we need to calculate the other values as well to use this chart. So we have got the value of DC over D as 5.4, so it will be somewhere here. That's 5.4 will be somewhere here. Then we need to draw a vertical line until we cross the appropriate L over D value. And L over D value here, we got L over D as 25. L over D as 25. The length of each pile is 7.5 meter, and the diameter of each pile is 0.3. So that will give us a value 7.5 divided by 0.3, that will give us 25, and the Poisson ratio in the problem is given as 0.5, and the H over L ratio is infinity. The H is the distance between the ground and the ridged stratum, and we have been given here that the stratum layer, assuming that the ridged stratum lies far below the base of the pile. So if you see a statement like this one here, far below the base of the pile, so we need to assume that it's toward infinity. So H over L ratio is infinity. So if we consider H over L ratio as infinity, then that will give us the value of the Poisson ratio. We need to use the 0.5, which are the solid line. So we draw a vertical line, and this is the 25 line. So that will be somewhere here. Then we draw a cross section, and that will be around 0.9, the RC value. The RC value will be around 0.5. So we have done from the RC value, which is 0.5, and we have been given the value of rho naught as 15 millimeter divided by 500 kilonewton, which is given in the problem here. A load test gave 15 millimeter settlement at 500 kilonewton, so we don't need to calculate the rho naught from scratch from the base equations, because sometimes you will given some values or some variables to calculate the rho naught value, or you will be given that directly using the load test values, which are the amount of settlements due to the certain load. So we need to calculate what's the amount of settlement due to 1 kilonewton by dividing these two numbers on each other. 15 millimeter divided by 500 kilonewton, so that will give us the amount of settlement due to 1 kilonewton, and that will be 0.03 millimeter. And then to calculate the value of rho naught prime, then we need to multiply by the value of RC to calculate the settlement of the cap unit, because we are interested here on the settlement of the cap unit, not on the settlement of the freestanding units. The freestanding units, it's the one we got directly from the load test, which is the one here, rho naught, and then we calculate the value of rho naught prime. That will be 0.027 millimeter per kilo Newton. And then we need to find what's the amount, because in here we have a pile group system. So we know that the settlement of a single pile will be affected by the settlement of the adjacent pile. So we need to find what's the contributions of the settlements from the adjacent piles and the settlements of the pile by itself. So to do so, as we can see, we do have here two pile group. We have the piles on the edges, and we have the piles on the center. So we can maybe name these ones on the edges as A. So this one will be A, this one will be A. So the one on the corner will be A, they will take the symbol of A, and the one on the middle will take a symbol of B, because in here we do have flexible foundation or flexible cap or flexible raft. So we know that the settlement of these pile will not be the same. So the settlement on the edges or in the corners will be less than the settlement on the middle. So we'll have a dip shape. So we need to calculate what's the value of rho A and what's the value of rho B. But we know that on the flexible settlement, we can consider the load on this pile will be the same. So the load on A will be the same as the load on B. So the load will be identical, but the settlement will be different on each pile group. So we're gonna have same load here. So the load on this pile will be the same, but the settlement will be different on the pile group A and on the pile group B. So we need to work out a table like this one here, and to work out the spacings between. So we consider firstly this pile, which is number 1, and we need to work out what's the spacings, and then to work out the spacing over D ratio for each pile, and then to calculate the alpha R value. So to calculate the spacings, for example, for this one between pile number 1 and pile number 2, it's 1.5 meter. Between pile number 1 and pile number 3, it's 3 meter. Between this pile and this pile, we need to take under the square root 1.5 square, 1.5 plus 1.5 square, all under the square root, and that will give us what's the spacings between pile number 1 and pile number 5, and it will be 2.121 meter. So after we calculated the amount of spacings, we need to calculate the amount of spacings over the emitter ratio. So that will be on this column, and then we take spacings over diameter with other variables to calculate the value of alpha R ratio. So we need to use this chart here to consider L over D ratio is 25, Poisson ratio 0.5, H over L ratio is infinity because we have the stratum, the rigid stratum lies far below the pile, the base of the pile, so H over L will be infinity. And then here we do have different value of dc over d. dc over d in our problem is 5.4, and then according to the value of s over d here, so we have here on the x-axis we have the value of s over d. So according to the value of s over d on this column, we can calculate what's the corresponding value of alpha r. So we calculate the value of alpha r from the y-axis. So we just need to draw a vertical line from the corresponding s over d ratio until we cross the corresponding value of dc over d, which is in our case 5.4. So it will be somewhere here. It will be somewhere here between these two lines. It will be between these two lines, and then we need to read the value of alpha r and to put the value of alpha r on these tables corresponding to the type of the foundations. And then we need to use the equations. So that's for the pile group, for the first pile groups, for the first type, which is A, and that's for the second type, which is B. So we took here pile 1, which is from a group A, and then we calculate everything with respect to this pile, and then we took pile B from type B, which is number 2, and then we calculate the spacing over D ratio and alpha r with respect to the second pile, which is of type B. And then we're gonna have two equations here, one with respect to the row A and one with respect to the row B. So if we put everything back into these equations, we can have these equations from the first group, from the first matrix, and then we're gonna have these equations from the second matrix. And because we have here the Raft system is flexible, because we have a flexible systems, as we said before, the load on the piles will be identical. So PA will be equivalent to PB, and that will be equivalent to P, which is the load on the piles. And then if we put the value of PA as the same as PB, so we can add everything inside the brackets into each other in equation 1 and equation 2. So we can add 1.72 plus 1.45, because this value, this symbol is the same as this one, because we have identical loading on the pile. So PA will be the same as PP, so we can put it as a P value. So we got here two equations. Row A, which is the settlements of type A of the pile, is equivalent to rho naught prime multiplied by 2.99 the load on the pile. Don't mistake these two simple with each other. This is the settlement, and this is the settlement value, row value, and this is the P value, which is the load value, the load on the pile, which is identical. And this is the row B value as well from the second equation here. We have the settlement of the pile B, which is equivalent to the rho naught B, which is the settlement of the cap unit, multiplied by 3.17 of the load on the pile. So we have here three variables, row A, row B, and P. So we need a third equation, and the third equation comes of them from the load carrying capacity of the pile group systems, which is 1.56. We have already calculated this value from above, if you remember, which is 1.56, and that will be equivalent to the load on the 6 pile. So that load is carried by the 6 pile here, which we have here 4 piles of type A and 2 piles of type B. So what we're gonna have here on this systems, we're gonna have in the third equation 1.56 meganewton is equivalent to 4 load carried by type A plus 2 load carried by type B, and we know that PA is equivalent to PP, so we can put these two values as P. So that will be 1.56 is equivalent to 6P, and we can find what's the value of the load carried by each pile, and that will be 0.26 meganewton. And if we found what's the value of P here, we can substitute this value here, the load carried by each pile, into equation 1 and equation 2, we can find what's the value of rho A, because we have already calculated the value of rho naught prime, if you remember, from the one of the steps above. It's 0.027. So we calculate what's the value of rho I, the settlement of the pile A, or of the type A, and the settlement of the type B as well. So that will be 20.99 millimeter, and that will be 22.25 millimeter. And because we have here, and as you can see, the settlement on the middle is a bit more than the settlement on the corners of the pile, because we have a flexible raft or a flexible cab at the top, which is distributing the load among the piles. And now to calculate the settlement of the systems, we need to take the average value, and the average value will be this value plus this value divided by 2. So that will be the average value of the pile group system. That will be 21.62 millimeter. So that's the settlement from the pile group. And then we need to consider the settlement from the raft alone. And to consider the settlement from the raft alone, we need to use this equation here. So we need to find what the values we need to substitute in these equations. The modulus of elasticity is given as 40 megapascal, so that will be as is. IS value will be 1.3 because we have a rectangle here, and the ratio of this rectangle is 5 divided by 2.5, so that will be 2. So the IS value will be 1.3 here, and the value of B will be 2.5 meter. The value of Poisson ratio is 0.5, so we need to calculate what's the value of Q. The value of Q here, because as you remember, we have a working load is 5, and part of this load is carried out by the pile group, and the pile group can carry 1.56 meganewton. So we need to subtract this load, which is carried by the pile group, and the rest will be carried by the raft. So we can consider here, because in here we have two systems, the raft and the pile group. So part of the load will be carried by the pile group, which is 1.56 meganewton, and the rest of the load will be carried by the raft, which is 3.44 meganewton. So what we need to substitute into these equations is the 3.44 meganewton, because this is the fraction carried out by the raft systems. Okay, so we're gonna put here, instead of the Q, we're gonna put 3.44, and then for the B value, I just need you to correct this value between the brackets and this value here. So instead of 1.5 by 2.5, I need you to put 2.5 by 5 meter. So we can maybe fix this thing here. So I need you to put between these two brackets. So this value will be, I need you to delete it, and then to put 2.5. So that will be 2.5 multiplied by 5 meter, because this is the cross-sectional area of the raft, 2.5 by 5, and that will be as well 2.5, because this is the width of the raft. Okay, so this is just a mistake in the solution, so I just need to correct this thing here, and everything should be all right. So 3.44 meganewton, which is the amount of load carried by the raft by itself. So this value here, and then we do have the Poisson ratio as 0.5. We do have the IS value as 1.3 as given from the table. We have the modulus of elasticity, or the Young modulus, as 40 megapascal, and that will give us 16.8. That's considering the wrong value, but I need you to recalculate these values, and to get new values it will be approximate to this value anyway. And then the whole and then for the two groups here, I just need to clear this one. Okay, so we clear this one now, and we close this one. Okay, so the settlement of the pile raft systems, the one due to the pile group and the one due to the raft. The first one will be 21.62 millimeter. So this is the one we calculated here, 21.62 millimeter, which is due to the pile group systems. 22.62 millimeter, and the amount of load here 1.56 meganewton, and then the rest of the load will be due to the raft, which we calculated here as 16.8. So that the 16.8, I just need to correct this value considering the new area here, and the amount of the ultimate load, or the load, the working load, is 5 meganewton. So the amount of total settlement will be, you need to add these two values together, so that will be around 38.4 millimeter. So that's the amount of settlement for the pile raft foundation system, because we have here two structure, the pile group and the raft. So you need to consider these two structure separately, and to calculate the amount of load carried by the pile group, and then to calculate the amount of load carried by the raft, and to calculate the settlement due to each load, to the one carried by the pile group and to the one carried by the raft separately, and to proceed with the calculation for the pile group as what we have done in the last lecture. So as what we have done here, okay, according to this procedure. So that to calculate the settlement due to the pile group, and then to calculate the settlement due to the raft foundations. And then for the whole system you need to add both values together, and that will give you the settlement for the pile raft foundation systems. And if you need to find out if the system will be enough to carry the load, then you need to divide the load carrying beer capacity by the working load, and you need to get a factor of safety more than 2.5. And for the settlement you need to check if this value is less than the maximum allowable limit here, because we need to check against the code values or against the maximum allowable limits, considering the structural load and the soil type, and then we can tell if this amount of settlement is fine, or if it's not fine. Okay, thank you. So we have done from the lecture tutorial today. If you have any question, please ask me on the chat, and we can maybe discuss if you have any inquiries.